Okay, shall we begin? All right. So our next speaker, first speaker of the afternoon here is Anton ZORITCH from the University of Paris City. He will be speaking to us on higher genus meanders and Masur Veech volumes. Please welcome.
Thank you very much for the invitation, and thank you for coming here. I know that in parallel there are several extremely interesting talks. So, I would like to speak about two objects which a priori have no relation, and I'm always happy when there are some unexpected relations. So I've seen at some point a web page of some linguistics department, and there is a picture, a famous picture of Babel Tower, and they are so happy that there are many languages and that there's human diversity. And for me, somehow what makes me usually happy is exactly inverse. When mathematicians find some universal language and are able to speak.
This is exactly what Buchstaber told me when people see similar pictures at different level in different languages, immediately a breakthrough comes.
Thank you. So now let me come back to the first object, so which is meanders. Meanders are just what you see in the picture. It's a smooth, simple, closed curve in the plane, transversely intersecting the horizontal line. And according to Landau and Zvonkin, the notion of meander was suggested by Vladimir Arnold. One can find meanders already in the papers of Henri Poincaré. They appear more or less everywhere in various contexts in mathematics, physics, biology. And a null conjecture and the null problem is to count them. Well, count with respect to very natural parameter, which is the number of crossings. So the crossings of this red line. And conjectural asymptotics is the one which you see, where surprisingly one can guess exactly the power of n, and one has only approximate value for the value of r. So this conjecture was specified later by the papers of Di Francesco, Golinelli, and Vitiev. And unfortunately, this problem is still open. Sorry. So how can one? Oh, yeah, sure. So one wants to count the number of meanders, and that's R is some constant, and one has only approximate values of this constant based on experiments, and one has reasonable guess for the power of alpha, which is seemingly somehow more difficult to catch, and one can apply methods of conformal field theory to guess alpha, and one can apply only numerics to put a hand on R. One can bound this R, and this I can explain in a second. So to get upper and lower bounds, somehow naive upper and lower bounds, one can apply the following method. One can chop a meander into two, cutting by this red line, and one gets a pair of arcs. And it is very easy to count the number of arc systems. That's just Catalan number. So one instantly gets an upper bound because just consider all possible pairs of arcs and mesh them together naively. And this is a square of Catalan number you get. Now, upper bound for R. There is a smarter lower bound, and this is based on their lemma of Landau and Zvonkin. They prove that for any, if you take, say, arc system on top, you can always complete it to a meander by some smart joining the arcs on the on below. So this gives low bound. So one can also compactify our plane, and in this case we get meander on a sphere. And each of the arc systems becomes arc system in the disk. So this is what we get when we compactify. And one can also, so this is another more topological interpretation of a meander. This is just an ordered pair of closed simple curves on a sphere, transversally intersecting, considered up to homotopy. Well, coming back, one has to make a marking, but this is a simple thing. So it is much easier to compute arc systems. And also, when you have an arc system and a disk, we can associate a dual graph to this arc system. And usually, one considers a combinatorial passport of the corresponding arc system because we have plenty of vertices of valency 2, like this one. Let's forget about them and keep track only of vertices of other valences, like leaves, this vertex of valency 1, or this vertex of valency 3. So one can start with these arc systems and glue them together. And the problem is that sometimes you get a meander, like on the left picture, or if you turn, you get just a collection of curves, as on the right picture. And I suggest the following, well, counting problem in a sense. Let's fix the combinatorial passport of arc systems on the northern and southern hemisphere. For example, let's consider, in this particular case, we consider this Mercedes sign graphs, or even trees in this case.
Maybe it's easier to calculate the whole generating function, not only for meanders, which give one curve.
Maybe, but can I stick to this problem? I suggest, so first let's start with simple-minded things. So instead of considering generating function, let's count just the probability to get a meander from pair of arc systems corresponding to, well, in this case, trees with fixed combinatorial passport. For example, here, by probability, I mean that I consider all arc systems of this type having at most n arcs, and I consider all arc systems on the right, all arc systems on the left. I assume that the number of arcs is the same, and then I also consider all possible twists, all possible gluings. And so in this case, so when there are only this number of arcs, I consider all possible twists, and then I start adding arcs. So when I considered all possible twists for these particular ones, I add arcs, and then I add more, and I consider, every time I consider all possible gluings, and for all these triples, I consider the asymptotic probability to get a meander after, from pictures like this. Now, one can ask whether this probability, so what is dependence on n? So whether it behaves like power over n, exponent over n. And I should say that personally, for me, the answer was unexpected. The probability is just a constant, as n tends to infinity, a positive constant. So that with positive probability, we get a meander. So just, we consider these complicated arc systems. We fix combinatorial passport, but for combinatorial passport, we consider these complicated arc systems. We consider random gluing, and all of a sudden, we get a single connected curve out of this thing. So I should say that here, the intuition is completely different compared to general meanders. So here I impose combinatorics of two trees. So if I do not, then probability would be 0. But here, when you impose combinatorics of the trees, the probability is not 0. And in particular, one can somehow simplify the problem and as combinatorial data, just memorize the total number of leaves. So for example, for this picture, our parameter would be 6. There are 3 leaves on one side, 3 leaves on the other side. But what counts is the total number of leaves, and you consider all possible arc systems with 6 leaves, and the limiting probability is expressed by the formula which you see well in this line. And in particular, you can fix this number of leaves and somehow split them as you wish into 2 and 4 or into 3 and 3 for trees with combinatorial passwords like this. It would be the same probability, which is explicitly calculated. So this is the answer which gets for this asymptotic probability for spheres. But one can play with meanders. Yes. So probably I was not specific enough at the first slide. All the results which are presented in this talk are based on joint results with Vincent Delacroix, Elise Goujard, and Peter Zorin. And yes, this is our theorem. So one can play with meanders not only in spheres. One can consider, so if we consider meander as a pair of transversally intersecting simple closed curves on a sphere, one can consider instead of a sphere, a surface of other genus, and one can consider also somehow curved systems. So and one can also, for surfaces of high genera, one can consider positive meanders, the pairs of simple closed curves which are intersecting positively. So as an exercise, I suggest to verify that the curve system on the left does not admit this positive orientation, while the curve system on the left is positively intersecting. And one also count meanders of, well, and arc systems on other surfaces. And here's the theorem from which comes all our count of meanders. So I suggest to count the following 3 quantities. First, so we fix the genus of the surface, and so this is one parameter, and we have to fix the number of bigons produced by intersections of pairs of multicurves. And the theorem claims that the following 3 quantities have all polynomial asymptotics. One can consider all pairs of transverse multicurves with at most n intersections and with exactly p bigons. So this is polynomial asymptotics where the degree of polynomial is 6g minus 6 plus 2p with some constant. One can count restricted, so a subset of multicurves, which was in the first line, namely one can count pairs where at the first place we have a simple closed curves, and at the second place some transverse multicurve with at most n intersections. It's the same polynomial asymptotics, so sorry, the same in the sense of degree of polynomial, it's the same degree. The leading term in the polynomial asymptotics is the same. The constant is smaller, of course. And one can count the number of meanders, meaning simple closed curve on the first place, simple closed curve on the second place. It is still polynomial asymptotics with the same degree of polynomial and with the even smaller constant, which I denote by C11. The meaning of the first constant, the geometric interpretation of the first constant, is up to rescaling by factor 12g minus 12 plus 4p, is the normalized Masur-Veech volume of the moduli space of quadratic differentials. The interpretation of the 2 other constants of C1 and C11 goes through count of square tile surfaces with certain geometry, which I will introduce shortly, and they're related to this Masur-Veech volume of the moduli space. And the 3 constants are related, so they are not independent. The proportion of this one cylinder square tile surface among all is the same as proportional of vertically and horizontally one cylinder square tile surfaces among horizontally square tile surfaces. So if you divide this constant by this one, you would get the same result as dividing this constant by this one. And a very similar result is valid for positive meanders and for positively intersecting simple, well, multi-curves, except that this time there are less objects like this. It's again polynomial asymptotics, but the degree of polynomial is 4g minus 3. But otherwise, the result is very similar, except that here, to get the first constant, we have to take the volume of the moduli space of Abelian differentials and not quadratic differentials. And I should say that while one can consider the previous problem somehow more restrictive or artificial because we had to add this extra parameter, which is the number of bigons. So in this problem, it's the only parameter is just the genus of the surface. So it's somehow, I would say, quite natural. And one more interpretation, since I already discussed the probability with which we get a meander out of two arc systems on two hemispheres by random gluing pair of hemispheres, one can consider, well, a braid on a surface of genus G-1 with two boundary components where each strand goes from one boundary component to another. So the number of ends of boundary components is the same, of strands is the same on each of the two boundary components. And we can consider a random braid like this and a random twist and glue it together. And one can ask, what is the probability to get just a single simple closed curve? And once again, the probability, asymptotic probability as the number of strands tends to infinity is non-zero, it's positive. And it is expressible in terms of the Masur-Veech volume of the moduli space of Abelian differential. So in this line, you have exact formula, and the values of these volumes are now known explicitly and can be computed in seconds up to genus 2000s. And asymptotic value of this constant is, as you see, approximately 1 over 4g, and all their terms of the expansions are explicitly known. So this asymptotic value is based on results of, it's our results plus results of Don Zagier and recent results of Amol Agarwal and parallel results of Chen Miller Zagier. So that was presentation of meanders and what we have for meanders. And now I have to introduce the other side. So I already mentioned square tile surfaces. So let me present square tile surfaces and somehow the way and Masur-Veech volumes. So to present Masur-Veech volumes, let me tell first what objects I consider volumes of what. So one can consider the moduli space of pairs where we have a complex curve, Riemann surface of genus G, and a holomorphic one form on this complex curve, Riemann surface, whatever you prefer, having zeros of prescribed multiplicities. So M1, M2, etc., Mn. So we know that in total, the holomorphic form on the Riemann surface of genus G has 2g minus 2 zeros computed with multiplicities. And you can split this number 2g minus 2. You can partition it to any partition, and you will get corresponding stratum in the moduli space of all Abelian differentials of all holomorphic one forms. So each stratum like this is modeled on the vector space, which is the first cohomology of the topological surface S relative to collection of points where we have zeros. And the latter vector space contains a natural lattice. So instead of considering cohomology with complex coefficients, you can consider cohomology with coefficients in Gaussian integers. And as soon as you have a lattice in a vector space, you have a unique volume element in this vector space, which is linear volume element normalized in such way that the fundamental domain of the lattice has volume 1. So you have God-given volume on each stratum like this, and so we have volume element in any space like this. Now, points of our stratum, well, these holomorphic differentials, they have norms. A holomorphic one form defines the area of the surface, and the norm is just the flat area of the surface defined by the corresponding holomorphic one form. Or in terms of these period coordinates, one can compute this norm, this area of the surface, as integral of omega bar, and it has a simple expression in terms of periods. So we have this quadratic expression. Any flat surface can be uniquely represented. So we can rescale your holomorphic one form in such way that the area becomes 1 and memorize the scaling parameter, real scaling parameter r. And in this way, we can define a volume element on the real hypersurface, which corresponds to Abelian differentials of norm 1. So basically, considering, for example, the entire moduli space of Abelian differentials not passing to strata, we have the following picture. So if we consider the entire moduli space of pairs complex curve Abelian differential, so this is a vector bundle over the moduli space of curves. So for every Riemann surface, we have complex G-dimensional vector space of holomorphic one forms. So the total space of a vector bundle is extremely non-compact by somehow trivial reasons, because every fiber is non-compact. Instead of considering the volume, so to define the volume of the space, actually we replace the fiber, which is a vector space, by a fiber which is a ball. So since we have a norm, we can consider unit ball in every fiber. And so when we are speaking about Masur-Veech volume of this moduli space, in reality, we consider the volume of the total space of a fiber bundle with analog of the total space of a fiber bundle with a fiber which is a ball, or a sphere, depending on their convention. And the theorem, which is still non-trivial, is that the total volume of any stratum is finite. The theorem is non-trivial because our base space, the moduli space of curves, is non-compact. So thus it is visible already for the principal stratum. But, so there is a theorem like this, yes?
So you're not taking the volume of the whole?
Yes. So, but you see the volume of the d-dimensional ball and the volume of d-dimensional sphere, they're related just by a dimensional factor. Well, my dimension changes. So do you agree that dimension of the unit ball in the Euclidean space of dimension d and the volume of the unit sphere in
I'm just saying it's about normalization.
well, somehow I'm trying to maintain normalization which respects the somehow spherical coordinates, and then the dimension of the space should be involved. It is not constant. It depends on the dimension. Yes. Okay. So now how do we count? So what I was saying is that dimension, well, the measure of this part of hyperboloid is related to the measure of the corresponding cone by dimensional factor, which is 2D. And how do we count volumes of figures? So basically, the standard way is to consider a mesh of rational points and to count number of rational points and then normalize. And this is the same as to rescale proportionally everything. So, and to count instead of rational points in a ball or part of a ball of radius 1, consider integer points in a ball of radius n. So what I'm saying is just trivial thing that to compute a volume of a ball or analog of a ball of radius 1, instead one consider a ball of radius r, compute the number of integer points inside, and then normalize by r power dimension of the space and pass to the limit as r tends to infinity. And that's exactly the same way in which we can count these Masur-Veech volumes. So the suggestion is to count integer points. Now, integer points in our case are points which are represented by integers in this period coordinate. And points which are represented by integers in period coordinates are flat surfaces which are glued from polygons with integer coordinates. So here, if you identify the sides of the corresponding polygon colored with the same color, you get a flat surface. One can check that in this case it would be flat surface of genus 2 with a single conical singularity, so a single zero of degree 2. And I claim that, this is a picture of kind of random integer point in our space. I claim that actually surfaces like this, their integer points are represented by square tile surfaces. So if you make several cuts and pastes, so I chop this triangle and put the top on the right, then I make one more modification, chopping this yellow triangle and putting on top, and you see that what we get is a surface which is tiled with squares. So my claim is that integer points in our moduli space which we are counting, well, the integer points in a ball of radius r, are actually square tile surfaces of given topology, or rather combinatorial geometry, because we fix the genus and number and types of conical singularities, tiled with at most n squares. So more formal proof, so that was kind of pictorial proof of the fact that integer points are represented by square tile surfaces. More formal proof is as follows. So if you have a point which in our period coordinates is represented by an integer point, I claim that the corresponding surface is endowed with our holomorphic form, is a cover of a torus where all branching points are projected to the same point on the torus. And the proof is as follows. So if we can fix one of the zeros over our holomorphic one form, and then we can map our Riemann surface to a torus, which is C over Z plus IZ, in the following way. Any point P is sent to the following complex number. You join our mark 0 P1 with a point P by any path, and you integrate our form omega along the path. You compute the resulting number mod Z plus IZ. This integral depends on the path, but if you choose another path, then the difference between two values would be integral over a closed cycle, and all integrals over closed cycles live in Z plus IZ. Since we mod out Z plus IZ, the result, we see that the result is independent of the path, and we constructed a well-defined map from our Riemann surface to a torus, and one can easily check that this is a ramified cover. So Analogously, one can define integer points in the strata of quadratic differentials, and basically the whole story is completely analogous. Now, let me present two results from dynamics, which I would use to finally construct a bridge between meanders and square tile surfaces in the next section, and to prove the theorems which were announced at the beginning. So, first I have to remind the notion of density and uniform density. So, so I will use the following structure which we have in our space. When we have any subset U in the stratum of, say, Abelian differentials, we have action of the group R plus, action of expansion or contractions on our translation surfaces. So we can apply dilation with coefficient t to any subset, and taking a unit ball of translation surfaces of area at most 1, if we consider this dilation by t, we get the set of translation surfaces of area at most t squared. Now, denote by hz the set of all integer points, the set of all square tile surfaces. We can define, so we have seen that we can define the Masur-Veech volume as normalized volume of the unit ball, where we take dilation of our unit ball by a factor of t. So this is a ball of radius t. We count the number of integer points which get inside. We normalize by t power twice dimension, complex dimension of the space. We take the limit, and by definition, the volume of the moduli space is 2d times this thing. Now, suppose that we have some subset of these integer points of square tile surfaces. We say that this subset has a uniform density, which is which is denoted by delta. If for any bounded open set in the stratum, we have the following property. So we take our subset U, we dilate it by a factor of t, and we take the number of integer points which live in our subset D inside it, and also we compare it, we divide by the number of all integer points inside this dilated space. If the limit exists as t tends to infinity and is the same, does not depend on U, then we say that we have a uniform density. So that our subset of specialized integer points has uniform density. So here's an example. If we consider all integer points in z plus z in the real plane, then the orbit of the point 1, 0 under the action of SL2z has uniform density. So this orbit is the set of coprime points. It's the integer points with coprime coordinates. It is known that their set of integer points with coprime coordinates let's compute the density. So first, let me compute the density of this set. Suppose that this set has density, even the uniform density. Then the orbit of the point 2, 0, that's the set of integer points having coordinates with greatest common divisor equal to 2. So this is the orbit of the point 2, 0. And clearly, the orbit of the point 2, 0 is obtained from the orbit of the point 1, 0 by dilation of the factor of 2. So the density of the new set should be 4 times smaller than the previous one. If we consider, so this blue points now are 4 times less dense. And if we consider the next point, 3, 0, then it would be 9 times less dense, etc. And altogether they cover everything. So this is kind of, well, a slightly cheated way to prove that the density of the initial set of this set of red points, or set of points with integer coordinates, coprime integer coordinates, has 6 over pi squared. To prove it formally, one has to use rigorously. One has to use ergodicity of SL2Z action. And then one really gets rigorous result on the fact that these coprime points have, red points have uniform density 6 over pi squared. Note that this set is somehow quite different from just a sublattice. Because if you go very far, if you go exponentially far from the origin, you can find islands of arbitrary large size where you do not have a single red point. Still, it does not prevent this red set to have uniform density because you have to go really very, very far to get such islands. So, and now we can define a family of measures in R2 in the following way. So here I am following the method which was used by Maria Mirzahani to prove her results on count of simple closed curves. So in this baby case, we take an open set U, and to define the measure, we do the following. We delay the set U by factor of t. We count how many red points inside this dilated set U we get. We divide by t squared. And so we get a family of measures. And by construction, a weak limit over any conversion subsequence is in the measure class of Lebesgue measure, because we're counting not all integer points inside the corresponding dilated subset, but only red points, so they're smaller number. So every ratio like this is bounded by their number of all integer points. And it means that where in the black, so any weak limit would be in the same measure class as just Lebesgue measure. And ergodicity of the SL2Z action on R2 now implies that the measure which we obtained as a weak limit converges to Lebesgue measure times this density coefficient. So now let me apply exactly the same idea to my more trickier space and to integer points in this trickier space. So consider the following horocyclic subgroups of the group SL2Z. So the group of integer upper triangular and group of integer lower triangular matrices. By definition, the SL2Z action preserves the set of squared out surfaces. Let us prove that for invariant sets under any of these two horocyclic subgroups, density is always uniform. So if we have a density subset which is invariant under any of these two horocyclic subgroups, we get a uniform density subset. Well, this follows from the fact that any finite SL2R invariant ergodic measure on any unit hyperboloid of a stratum of Abelian differential is ergodic with respect to the action of this discrete parabolic subgroups. And this is just a consequence of Moore's ergodic theorem. So in our case, the situation is particularly simple because SL2R is a simple Lie group. So this is just a direct corollary of this ergodic theorem. Now, what subsets, what would be my analogs of this red set of integer points with co-prime coordinates? I will consider square-tiled surfaces with fixed number of horizontal cylinders. So here you have a square-tiled surface, and if you consider their horizontal trajectories, they all are circles, and we see that the upper part of our square-tiled surface is swept with circles of length 2, and then there is a critical leaf, and now our circles become like this. So they have length 1, 2, 3, 4, 5, 6. So in this case, our square-tiled surface has 2 horizontal cylinders, and actually in this case 2 vertical cylinders. Now, if we apply an element of our horizontal group, so for example, well, this generator, then our square-tiled surface is transformed. We get a new square-tiled surface. So after regluing it, we get again square-tiled representation. We see that this action does not change decomposition into horizontal cylinders. It do change the decomposition in vertical cylinders. It does change the decomposition to vertical cylinders. But horizontally, the number of cylinders does not change. And from the previous theorem, we see that if the contribution of, say, 2-cylinder square-tiled surfaces, the total contribution to the volume is non-zero, that meaning that if their 2-cylinder or 5-cylinder square-tiled surface has positive density, this density should be uniform by the previous theorem. The fact that for any, that all these contributions, so there is an elementary topological estimate on how many cylinders might have a square-tiled surface in this or that stratum. And for all integers between 1 and this upper bound, it is easy to check that the contribution to the volume, the global contribution, is positive. So the density is strictly positive, and it means that all these densities are uniform. So it means that in particular for our tasks, it means the following. You can compute this asymptotic proportion, this contribution to the Masur-Veech volume of integer points, which comes specifically from k-cylinder square-tiled surfaces, and denote this value by pk. So this is asymptotic proportion of k-cylinder square-tiled surfaces among all square-tiled surfaces. And now you can take any small domain in your moduli space and consider integer points only in this, well, rational points only in this small domain, and compute asymptotic proportion in this small domain. It would be the same as for the entire space. So this is, I'm just rephrasing the definition of uniform density. Okay, and also I need one more result. One can consider k-cylinder surfaces horizontally and g-cylinder surfaces vertically. One can check that, so we have just seen that our density can be interpreted as a probability to take a random square-tiled surface and to realize that it is horizontally k-cylinder. And I claim that the conditional probability to take a horizontally, say, j-cylinder surface, consider its vertical decomposition, and the probability to get a k-cylinder surface among these restricted square-tiled surfaces is the same as just probability to get a vertically k-cylinder surface among all square-tiled surfaces. So there is no correlation there. The horizontal decomposition asymptotically doesn't know anything about vertical decomposition. So this follows from the fact that, so that's the relation which I need. And this follows from just from the structure of our period coordinates. The period coordinates are coordinates, so this homology with complex coefficients. It can be represented as direct sum of real part and imaginary part. And actually, the real part is completely responsible for vertical decomposition and this one for horizontal decomposition. And they do not speak to each other. So this result is particularly simple. And now I can finally construct my bridge between square tile surfaces and meanders. So I prepared everything, and I can merge these two objects and somehow. Now, my goal is to convince you that actually it is the same object. So if we have a square tile surface, then we can construct a circle passing through the middle of the square for every square. We get finite collection of circles. We can also construct corresponding vertical circles. And what we get is a pair of multi-curves. So here, my square tile surface is square tile sphere. I get a transverse pair of multi-curves on the sphere. For the sphere case, from any transverse pair of multi-curves on the sphere, I can construct a square tile surface. So they are in bijection. Well, for other genera, the situation is slightly, so I'm just considering dual graphs. So for, and probably here I have to let you watch this picture for several seconds because the statement is completely simple-minded. So basically, my claim is that for spheres, there is a bijection between I think that it doesn't merit attribution to Thurston. It's really completely trivial facts.
Looks like a representation of nodes by 3 times.
I think that everything is this is really much more basic. It's really a simple-minded observation. The Thurston construction. Well, yes, it is kind of particular case.
Does it have anything to do with diagrams?
No. No. It is not three-dimensional. It's way more basic. It's really completely elementary. Thurston construction, basically, it's the base of constructing related pseudo-anosov and so on. I do not consider here transformations yet. So yes. Yeah. Yes, I agree. It can be considered as part of this Thurston construction. Well, in high genera, there is no bijection, but asymptotically almost. So in high genera, the asymptotic count of this square tile surface and pairs of transverse multicurves is the same. Because most of multicurves, which somehow, most of square tile surfaces which you would read out of pair of multicurves would be as you want. So when you fix the number of bigons and the genus, the difference would have smaller order. And now we can just read the description of pairs of multicurves in terms of square tile surfaces. So the ones where we have a single multicurve, when one of the multicurves has only one component, it corresponds to square tile surfaces where corresponding decomposition has only one band of squares, say, horizontally. And meanders, so pairs of multicurves where you have a single horizontal component and single vertical component, that's square tile surfaces containing a single band of squares horizontally and single band of squares vertically. So, and we already know how to count them. So for genus 0, you do the following. So first step is you have just natural bijection between pairs of multi-curves. And so you just translate everything into the language of square tile surfaces. We're interested in the number of meanders. So we know that asymptotic count is polynomial with the same degree of polynomial, and only coefficients are different. We're interested in the coefficient C11, and we have seen that there is this proportion, so you can express this C11 as C1 squared over the volume of the corresponding moduli space. So I recall that we can count multi-curves. We can count all square tile surfaces. We can count separately square tile surfaces which are horizontally one cylinder and only single band of squares. And we can count even more restricted count is horizontally one band and vertically one band. So this is horizontally one band and vertically one band, and it can be expressed in terms of this is count of everything, and this is only horizontally one band. So everything is the Masur-Veech volume. Horizontally one band is somehow relatively easy to count, and as a result, we get the formula. And in genus 0, genus 0 is particularly lucky because there is an explicit closed formula for the Masur-Veech volume, and we get this simple answer. But in general case, we get a result which is expressed in this Masur-Veech, in terms of Masur-Veech volume of the corresponding stratum of quadratic or Abelian differentials. This is not, well, there is a whole story of evaluation of these Masur-Veech volumes. So first, several values we have obtained with Kontsevich using combinatorial methods. Then Eskin and Okunkov found a much more efficient approach through representation theory. And recently, there were spectacular results due to Chen, Müller, Sauvaget, Zaghir, and separate and independently by Amol Agarwal for large genus asymptotics. So now, for Abelian differentials, basically the picture is quite complete. For quadratic differentials, not yet. For strata, we still have little knowledge of volumes, but for the principal stratum, we have pretty good knowledge due to two alternative formulas. So one through Witten Kontsevich correlators and another through Hodge integrals obtained by, so through Witten Kontsevich correlators, it is the formula which we proved with Delacroix, Goujard, and Zograff, and through Hodge integrals is the formula by Chen, Müller, Sauvaget. And there is large genus asymptotics proved by a spectacular proof by Amol Agarwal, who is speaking today later. So you can, well, he would be speaking about different subject, but still. Yep. Oh, yeah. So, and I think that probably I should chop Arnold's problem. It is somehow similar. There was an old Arnold problem about interval exchange transformations with integer parameters, and basically it is the same objects. Thank you very much for your interest.
Oh, do we have questions? Yes.
So what about you consider meanders that can be tangent to the equator? You add additional tangent conditions, number of tangent points. First, you may think you perturb a little bit, it will become like actual like 2-point intersection, but it seems like that would change if you have many such tangent points. If you go up or go down, seems like some kind of alternating counting that might lead to some also interesting combinatorial identities.
Meanders with tangencies.
Yeah. Thank you for the question. I never thought about this, but my first impression that yes, it can be counted. That so if you are in the same setting as here, that it would correspond probably to even to some strata, and that there would be everything should be parallel with polynomial asymptotics. But it is kind of irresponsible answer. I never thought about this. It's just first impression. I have to think about it more seriously.
I have one comment and one question. So first, triangulations of a polygon live in the center of mathematics. So they have combinatorics, topology, and everything else through Stashev polytopes, which are related to everything. Just Catalan numbers and then Stashev polytopes and so on. And meanders seem to be something like pairings between two parts. One part is something which is counted by Catalan number on one side, and the other is counted by Catalan number on the other side. So we do have something in the center of mathematics in on one side and something dual. So this is a comment. And my question is, so you mentioned Zagir many times. So do your computations have anything to the famous Harer-Zagir theorem?
Well, the short answer is yes. The slightly longer answer is that he has a completely, I would say, forgotten paper where he has a shortened combinatorial proof of related to Harer-Zagir formula and to Frobenius formula, and that's what we were using. Yes.
Any more questions? I have actually three, but first one, a comment, a beautiful presentation. I was wondering, did you just give an elementary proof of Teichmüller's flow using this SL2Z action? Because it seems that you can prove ergodicity.
No. I'm using ergodicity of SL2. Oh, I'm using.
Yeah, but you're using it at an elementary level, and it seems like okay. That we can discuss.
I'm using ergodicity of SL2R action or SL2Z, and then I'm using more.
You're using
okay. I already have ergodicity of a larger group to deduce ergodicity of the subgroup.
Okay. One question is the theory of rests on square tile surfaces, and I really feel strongly that this could be arithmeta, as number theorists will call it. I would like to think of an application is if we were to be counting closed geodesics on the moduli space, including large genus. Like I'm not fixing the genus, and I would like to count closed geodesics which pass through square tile surfaces. I wonder if that could be done, and if it could be done, then now you could classify closed geodesics. Each closed geodesics, as soon as Nosov has a trace field, and you can replace Gauss integers with some other quadratic field, and you restricted, more interesting counts of closed geodesics. Think about it.
I'm not 100% sure that I understood the question, but I'm afraid just my somehow first impression is that I'm frightened because you have this dense set of integer points.
Yes.
You have plenty of arithmetic technical curves in any stratum, and you have only finite number of non-arithmetic technical curves usually.
Yes,
So-
usually, but not genus 2.
Yes. So yeah. Oh, you are speaking concretely about genus. I don't know.
I mean, not yeah, the quadratic ones, degree 2, not genus 2. Degree 2, there's infinitely many technical curves. Okay. Any more questions? Oh.
Thank you for your excellent talk. And I have a question about the large genus asymptotics, about the intersection number on the moduli space. The proof by Amor is based on Varasava constraints, and I wonder to know that is there some practicable ways to see the large genus part from the generating function, corresponding to the ribbon graph expansion, ribbon graph enumeration, and array Laplacian transform of array function.
One can address the question to the author, but for me, I was already extremely happy with Amor's proof. I somehow I do not see any approach to read it out of the generation function, right? Just any instant approach. I would be happy to have one because let me see. It might help, for example, it might help to get large genus asymptotics for for smaller strata, which we do not have right now. Well, we have to know about more intersection. You have to know more intersection numbers, but still somehow it would be great, but I do not know how to get it.
Oh, thank you.
Okay, I think our time is pretty much up. Let's thank Anton one more time for a beautiful talk and insightful answer.
Okay.
Okay.